We'll begin here with mass spec. Okay guys, top of the hour, let's get started. The substitution handout I sent you was an outdated copy, older PDF. I've just given you a new one here. I did not include the sort of the first page, front and back, or the very last page. I'm only giving you the outline section. Okay. So keep the one you printed out as well. There's been a few updates. Okay, we'll have a quiz soon on, what do we got since test 2? We have resonance. Okay. In the resonance, there were questions to be working on. I sent you the answer key by email. Okay, very important questions. We moved on to dienes, 1, 2, 1, 4 additions. There were questions there. Diels-Alder. Okay, I think the answers to those questions were in the back of that packet, the answer key. Any questions you have there? We're doing mass spec. We started that in lab. We're going to continue that here now. And now we've also begun our substitution reactions. Okay? I'm giving you the revised handout today. Okay guys, any questions about lab this week, including group lab report we're working on from last week? No? Okay, mass spec. We introduced mass spec. How do you get a mass spectrum? The idea of ionization of the molecule, make molecular ion. The molecular ion could hit the detector and give you a mass for that. Or it can fragment. Fragmentation, very important. Let's look at examples of fragmentation and examples of mass spec. We'll start with the simplest type of compound. An alkane. What's that? Hexane. Molecular weight is 86. Okay? You add up the molecular weight. We're doing just nominal mass, whole number mass. So we're not doing 86.139 or whatever. It's 86. Later on, we'll mention high resolution mass spec where you get 4 decimal places. Right now, just whole numbers. Basic mass spec. Here's your mass spectrum for hexane. We do have a molecular ion at 85. What is that? 1, 2, 3, 4. Okay, that's 5. 86 molecular ion. Okay. The rest is fragments. Our base peak is where? Now minus 29, which is 86 minus 29 should be what? 57? Indeed, it is 57. Base peak. Okay. What could base peak be? Now in this example, it's not intuitive of where we're going to cleave. Ultimately, when we start cleaving, we're going to look for the most stable cation. Anywhere you cleave here, it's always going to be primary. We said primary cations are bad. Yes, in mechanisms, but in mass spec, you're going to see primary cations. Okay? So we got a peak at 57. What could that be? Well, 57 is loss of what from this? 29?
29.
Okay. 29 is a common number for an ethyl group. If you think about it, if we cleave an ethyl, cleave here, to give this cation, okay? Now we're talking about cleaving the molecular ion. So we got to ionize it first, and it's a radical cation, right? Everything we're talking about is a radical cation. It's the thing that cleaves. And when a radical cation cleaves, what does it give? A radical and a cation. This could be the cation, and minus 29. The other fragment would be the ethyl group, and that would be a radical. We're not looking at mechanism for this cleavage. other than just a radical cation cleaves to give a radical and a cation. Of these two, only the cation shows up, right? The mass of this, M minus 29, because this should be 29. That's 2 carbons. 2 carbons is 24. How many H's here?
5.
There's 3 on the end, and there's 2 here. We didn't lose any when we cleaved, and we didn't gain any. There's 5. 24 and 5 is 29. This is 29. Thus, this is M minus 29. An ethyl fragment, an ethyl radical is common 29. A methyl radical would be 15. Ethyl 29. We'll keep growing. Common fragments. M minus 29. Now, the mass was what? 86 minus 29 should be 57. Indeed, that's 57. And that is what we can say that this peak is for. How else would you get a 57? I don't see it. Is that the best cation you can get? That's the only cation you can get here. It's always going to be primary. Okay, so that's A, that's A. What if we had cleaved here? What would that have given? That would have given boop, 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 boop. That cation plus what? A CH3 radical. What would this be? It'd be M minus 15. Again, what do we got? 86? 86 minus 15 equals what? 71? Do we have a peak at 71?
Yeah.
Yes, right here. And so that's that. We can cleave at a variety of places here, and you're going to see peaks. I'm not going to go through much more. Basically, you see lots of peaks here that could come. Look at the mass spectrum below. The mass spectrum below is a lot cleaner, a lot simpler. This compound has a mass of 114. Look, is 114 showing up? Apparently not, or it would have been cut off. Apparently there's nothing here. No molecular ion. Sometimes the molecular ion doesn't survive long enough to hit the detector. Okay. Let's consider this as a molecular ion that is a radical cation. Where would the radical cation most likely cleave? Here again is the answer. You're going to cleave, predictably, to give the most stable cation. Where would you like to form a carbocation at in this molecule? Tertiary site. Right here. So what if we cleave here? What would that give? It's going to give this cation. Now, keep this in mind. We say cleavage gives a radical and a cation. We could put the cation on the left or the right. If we put the cation here, that's going to be radical. If we put the cation here, that's going to be radical. Which side do you want to put the cation? On the left. So you make this cation plus that radical. And that's a potential cleavage. This is a pretty large fragment, so it's almost just as easy to add this up. This would be 4 carbons. 4 carbons would be 48. How many H's here? 3, 3, and 3. 0 H's there. 9. What is this mass? 57? Is this peak at 57?
Yes.
55, 6, 7. Yes. And it's the base peak. The reason there's fewer peaks down here is because this molecule cleaved predominantly in one location, because it was such a favorable cleavage to make a tertiary cation. Where up above, it cleaved a variety of places, because anywhere it cleaved, it was going to be primary. Let me ask you this. Is there another way to cleave here to get a tertiary carbocation?
You wouldn't take off one of those methyl groups.
Well, yes. If we cleaved here, what would that give? Boom, 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 boom. It would give cation there and a CH3 radical here. Now this would be M minus 15, because I know that's 15. And mass was 114, so this should be what? 99. Do we have a peak at 99? Yes. So this is this here. Question. Why apparently this did not cleave as much, because there were less ions generated, and thus we got less current generated and less signal generated. Why was this pathway not as favored as the other pathway? They both gave tertiary carbocations. The answer involves looking at the radical part. Just because it doesn't show up in the mass spec doesn't mean it doesn't show up in the thermodynamics of the cleavage. That's a methyl radical. What type of radical did we make above when we made this? We already erased it.
Butyl radical?
Yes. We made this. This radical, is it primary, secondary, tertiary, what? It's primary. What is this radical? Primary, secondary, tertiary?
Nothing. It doesn't
It's
exist.
parent. It's neither. Now the stability of radicals is just like stability of cations. A radical is electron poor. It's stabilized by induction. Primary, it has one rich friend donating. This has 3 rich friends donating. How many rich friends does this guy have donating? It's not even primary. The reason that this pathway did not occur is not because of the cation. They're essentially the same, both tertiary. It's because of the radical. This gave a better radical. Even though it's primary, it's better than methyl radical, which is worse than primary. It's called parent. It's not even primary. So that's the reason why the other pathway gave the base peak.
Are you saying parent?
Parent.
Parents.
Parent, like
Like
sons, daughters, and parents. Parent meaning like the original, or from there you get primary, secondary, tertiary. Starting point. Okay. We could have discussed the same thing above. Sometimes your radical will make one peak more prone. Let's look at isotopes a little bit in mass spec. Here we have 1 bromopropane, or maybe called 1 propyl bromide, or N-propyl bromide. Variety of sort of names, slang names. IUPAC would be 1 bromopropane. First off, what's the molecular weight of this compound? Is it 122? Or is it 124? It's both. Because bromine has a major isotope. Bromine, when you add up molecular weight for this compound, what would you use for bromine?
80.
Would you use 79.904? You typically would. But that's when you're adding up molecular weight for a bulk sample. Mass spec looks at individual molecules. And an individual molecule meaning one bromine in the molecule. One bromine does not have a mass of 79.904. That's an average of all the bromines in the world, the natural world. Mass spec, you don't see an average, you see individual. Bromine either has a mass of 79 or 81. Okay? If you round this off to whole number, that's 80. No bromine has a mass of 80. It's either 79 or 81. So, is the molecule you're looking at, is it 79 or 81? Well, it can actually be both. Because what's the natural abundance for the two? It's about 50-50. Half the bromines in your body are 79, half the bromines in your body are 81. And we have to just deal with it. So it's both. It's 122, and it's also 124 when the bromine is 81. Okay? We do a mass spec of this. Do we get the molecular ions? Yes, right here. 122, 124. You get them both. If you're dealing with a natural sample. Because if we inject this sample into the mass spectrum, or into the instrument, you obviously have to inject more than one molecule. It's impossible to inject only one molecule. So you inject a huge number, even if it's sweet little bit, it's a huge number. Of that huge number, you're going to have about 50-50, 79, 81. And you basically have a mixture of, you could call it two different compounds, but what we're dealing with here is isotopes. Okay? Natural isotopes. And both molecular ions hit the detector. Importantly, though, the natural abundance is 50-50, and so the peak height is about 50-50. Now, give or take some experimental error for the tuning of the instrument, etc. How good is your instrument? But if you have a super finely tuned instrument, that's actually one way that you can determine the natural abundance of some odd element by doing mass spec. But that's already been done. Okay. Now, how could this molecular ion cleave? Well, I've given you a proposed peak over here. Just that cation, that comes from just cleavage here to give that plus what? Bromine radical. Now your halides often like to form radicals. And so what's the mass of this? It's M minus 79, but it's also M minus 81. Might be easier just to add it up. 3 carbons is 36. And what's that, 7? What's this, 43? Is that 43? Note that this signal, by the way, the 2 peaks over here, this is called your isotope pattern. Now, for bromide or bromine, isotope pattern for bromine is about 50-50, equal height. Look at here. That looks like an isotope pattern. Does this have an isotope pattern to it, this peak at 43? Do you see one, by the way, this is often called M and M plus 2. I mean, we see a mass for this fragment. Do we see an M+2 to go along with it? That tells you there's no bromine with it here. But of course there's no bromine because we're down at 30-something. Bromine itself is 79. But to me, this looks like there's bromine associated with this fragment because there's a twin there. There's an isotope pattern here. This is at what? 105, 6, 7? What is this? 107, 109? Let's see, if this lost 15, if you added 15 to this, that would be what, 122, 124? Does this take us back to mass? 122, 124? Yeah, I think this is where we lost a CH3 radical. And if you lose a CH3 radical, from the end you would get that cation, right? What's the mass of this cation? It's 107, right? But it's also what? Also 109. It's got two masses. And what would be the ratio of these two? 50-50, and there you go. It's about 50-50. And so, but I saw the isotope pattern. That's the first thing I saw there. It also looked like isotope patterns here and here. Oh, by the way, what do you think this is? That's almost like a double isotope. I don't know why it's double. This could just be bromine cation. I don't know why it would be a cation. That's a little odd. I wouldn't get into that. But it's possible. Y'all can see a lot of weird things in mass spec because it's a pretty high energy process. Okay, you're zapping it with electricity and then the molecule flies apart. All right, so isotope pattern. The one below is chlorine. Chlorine is either 35 or 37. For chlorine, the natural abundance is 3 to 1. 35 being 3. 3 to 1 ratio. So down here, we see a 3 to 1 ratio for our isotope pattern. I see a 3 to 1 here. It makes me think chlorine is in the fragment. 63. Something may not be right here. It's always wrong and I never correct it. Is this right? I don't think. First off,
No.
let's see if we can check it. If we go from here to here, that's a loss of
49, what should be 49?
78 to 63. 15. That's a loss of a methyl. If it lost a methyl, it should be it's here. This is missing a methyl here. And this should be 63. But it should also be 65. It's 63 when the chlorine is 35. It's 65 when the chlorine is 37. What's the ratio of these? 3 to 1. And that's what you have here. By the way, is this cation even on the spectrum? This cation would be loss of 29, wouldn't it? Loss of an ethyl, 29.
So it should be around 51? Did I do that? 37.
80 minus 29 would be 51. It should be 49, 51.
There's a little bit of a shadow there. I don't know if that.
You see, it's not much there. I'm very surprised that this cation is not there at all. What's the base peak? some reason, the base peak is this guy here. But they're both primary cations, so why would you form one over the other? We could look at the radical. Yeah, when we formed this, what type of radical did we create?
Primary.
Methyl radical. But when we formed this, what type of radical did we make? Chlorine radical. And the halides tend to like being radicals sometimes. That's why a lot of the freons and the halogenated compounds form radicals in the atmosphere, and the radicals react with ozone, deplete the ozone. I'm not sure why halogens like being radicals. Hard to understand radicals sometimes. Okay, let's start looking at compounds that have hetero atoms. This being an ether. Here we're going to get more and more predictable in the cleavage. Okay. Does oxygen have a common isotope? No. Your common isotopes are chlorine and bromine. Chlorine does not have a natural isotope. All fluorines are 19. You can make fluorine 18. It's man-made. It's used in PET imaging. It's not natural. Iodine, let's don't get into that. Mainly 127. Somebody say something? Oxygen, no. O17 is an isotope of hydrogen, but it's very, very minor. Okay? What do you want to use for oxygen here? 16. And if you use 16, it adds up to 74. What are we using for carbon? 12. Okay. Speaking of carbon, let's go back over here. It may not show up well. Back over here, there's a peak at 87. That is a peak, because otherwise the baseline's flat. What is this at 87? The mass is 86. But 86 comes from
Carbon 13?
12 times 6 is, what's that, 72? And we got what, 14 H's? 14 H's equals 86. And that was our 86. Where's the 87 come from?
Carbon 13.
Carbon 13. What's the natural abundance of carbon 13 in natural sample of carbon? Percent. We said it on day one. About 1%. See, that's so small, you typically don't even mention it. And so the ratio is basically 99 to 1. Now this looks more than 99 to 1, but that's from where one molecule has a C13 in it. What's the chance of one molecule having two C13s? You can do this math. That would be 88. And so, is there anything at 88? It depends on the sensitivity of your instrument. What's the chance in nature of, when you buy hexane, what's the chance of one molecule of hexane having all C13s? There's some chance. It's quite low though. If you pick up a bottle of hexane, there's probably one molecule in there that are all C13s out of a gazillion. If you inject it, problem is the instrument is not going to be sensitive enough to see that. And so you're not going to get a peak at 92 for that one molecule. Everybody with me?
What about C14? What's the abundance of that?
C14 is just noise. You're not going to see it. I don't think you're going to see it in mass spec. Although remember, anything's possible, there's exceptions to everything. You'd have to look in the literature. Does anybody ever observe C14 by mass spec? Probably it's been observed, but it may not be routine enough to commonly. Again, all these isotopes of elements, nowadays they're observed by mass spec. Very sensitive. We're talking high dollars. Okay. Not your Walmart mass spec. We're talking about Neiman Marcus, high-end mass spec. Pay for that sensitivity. Okay, so let's look at this. We're going to look at what's called alpha cleavage. It's just a term for where we're going to make cations. And we're going to bring in resonance here. We're going to cleave to put a cation, make a cation that's resonance stabilized. And if we cleave here, this will give this cation plus a methyl radical. This looks like a primary cation, but it's way better than that. Why is it better than just primary? Because we can do resonance. Boom, boom. Right? And we can put the charge on oxygen. Resonance. 2p orbitals here. All that theory. We're going to make resonance stabilized cations. This is called alpha cleavage because we're putting the cation, alpha meaning sort of the first atom next to the lone pair. Okay? Alpha cleavage. Cation, I think this definition is going to hold up. Cation next to LP. This is known as alpha cleavage. All right, that's what we would predict. There's other peaks here. The base peak, for example, I think on this one, I don't know what the base peak is. It's quite odd. It's not predictable for me. Let me ask you this. What if we cleaved over here? We could put cation there. Would that be any different though? It'd be the same exact outcome because it's symmetrical. Everybody see that? But in the next example, maybe we could cleave over there and it would be something different. This is what we predict here. Let's move ahead. When you run an IR, do you predict every single peak in the IR? Do you interpret every single peak? No, especially not the fingerprint. Same thing with mass spec. We're not always going to interpret every single peak. Let's look at ones that we do predict. Down below, what do we have? And a mean. It's a primary mean. Okay, first off, it's much simpler mass spec. Something was very predominant. I've already given you the answer here. This guy apparently cleaved here to give that cation plus that radical. Why this cation? Well, it's next to a lone pair. We can do resonance, correct? So it's a resonance stabilized cation. It charge is delocalized. So this is a good cleavage site. And what is this peak? 40? Oh, we need to talk about something here. This cleavage peak is that 44? It's even. It's not negative, it's even. You can add this up, it should be 44. It looks like the molecular ion was, well, almost absent. What is it? 101. That's odd. If you've been paying attention on the previous ones, I know you haven't noticed this, the mass of all of our previous examples was even. This is the first one we've had an odd molecular weight. I reckon that's 101. It's almost absent. Because the molecular ion that's formed with the ionization method, it apparently breaks apart real quickly and never reaches the detector. The detector's over there. Here I go. I broke apart. And so when I hit the detector, I've already broken apart. Why did it break apart so easily? It's making a nice cation. Not only is it making a nice cation, it's also making a tertiary radical, which is the best type of radical you can make. Although you could do resonance of radicals. Here we go though, nitrogen rule. If you have an odd number of nitrogens in your molecule, your molecular weight's going to be odd. If you have an even number of nitrogens, or zero being an even number, your molecular weight will be even. Compound above. How many nitrogens in the molecule? Is it an even number or odd number? It's 0. 0 is an even number in this. So the molecular weight of the above compound should be even. Indeed it is, 74. Down here, how many nitrogens in this compound? Even or odd? Odd number. Your molecular weight is going to be odd. Not only that, when you cleave, an even radical cation cleaves to give odd cations. So all the cations before were odd, like 45 and 31. But down here, when you cleave an odd molecular ion, you get even cations. You think about it.
Is that only with nitrogens?
Do what?
Is that only with nitrogens?
This rule, it's probably with other things. It may be with phosphorus. I'm not sure. If we had a mass spec guru, they could tell you. Nitrogens is of the common things. Called the nitrogen rule. How could you use this? What if you were isolating natural products, like from mushrooms or something, or you're investigating their psychedelic properties. You got some new compound from this mushroom growing in your backyard, and you do a mass spec. You don't know what the structure is. You've purified it. How do you know it's pure? TLC shows one spot maybe, after you did some purification. Now you're going to try to figure out what it is. You do a mass spec, and you get a molecular ion of 864. What does that tell you about the number of nitrogens in your compound?
Even.
Even number of nitrogens. It either has 0 nitrogens, or it's 2, or it's 4, or it's 6, right? So right there you have a little bit of information about your structure which may otherwise be unknown. Nitrogen rule. By the way, is there another way to get a good cation here? We made this cation. What if we had cleaved here and instead of putting cation here, we put cation there? Is that reasonable to put cation there?
Mm-hmm.
And put radical here? I don't know, that's a pretty good cation. What's the mass of this? 4 times 12, 48. And 9, is this 57? Do we have a peak at 57?
Yes.
Yes.
A little bit.
Yeah, I was hoping it'd be a little bit bigger than that, because that's a good cation. But apparently it liked going this way better, because this is a resonance stabilized cation. That is 57. If I get the math wrong, please correct me next day or something. I think it's 48 and 9. 3, 3, and 3. Okay. Let's look at aromatic compounds, compounds with double bonds. Sort of a variation of alpha cleavage, cation next to LP, or pi bond. Basically, how can we do resonance? We can do resonance with long pairs. You can also do resonance with pi bonds. usually carbon-carbon pi bond, because if it's a carbon-oxygen pi bond, you gotta be careful. You don't want to leave oxygen without an octet, right? Okay, let's look at these two. Basically on this page, these two are isomers. Top compound, bottom compound. They both have mass of 120, same formula. But we expect the mass specs to be quite different. Here, our so-called alpha cleavage, we're going to cleave here to give cation there plus what? Plus an ethyl radical. Now be careful with your cleavage. This is 6, 7, 8, 9 carbons. A lot of times you guys will end up with 10 carbons after you cleaved, because you'll want to draw this like that or something. Make sure you get the number of carbons right. That's a 2 carbon right there. Why is this a good cation? Okay. By the way, what's the name of this cation next to the aromatic ring? Benzylic. Benzylic cation. And we can do resonance. The pi bonds aren't drawn in that precise, but we can move them out here. We did resonance before. You cation here. Okay, and you can keep doing resonance. Look back at your resonance. Very good benzylic cation. So this is what? M minus what? 29. An ethyl radical is 29. Because it's 2 carbons is 24. 3 and 2 is 5. 24 and 5. 120 minus 29 should be 91. Is this peak at 91? Yes, and it's predominantly the major pathway, major cleavage. Down below, you're going to lose not 29 but 15. Because you cleave here, you get this plus the methyl radical. This is M minus 15. 120 minus 15 should be 105. Is this 105 here? No, we're not cleaving something. We're not making a cation right on the ring. Okay, ready to blow your mind. Boom, boom. That cation is not resonance stabilized. You guys tend to think just because it's close to all these pi bonds, it's resonance stabilized. It's not. Try drawing resonance structure. You cannot. That's not, okay? But benzylic here is. You can draw resonance structures, several. Okay? No, bad. Mess you up. Benzylic cation. So, if you were given these two spectra and the two compounds, could you match each compound to the correct spectra based on where you predict cleavage? The top one I expect to lose 29. The bottom one I expect to lose 15. Carbonyl compounds will also do alpha cleavage. We'll put cation next to lone pair. This is a ketone. Molecular weight of 86. It's going to look a little bit odd, but we're going to cleave here. And we're going to put cation next to lone pair. There just happens to be a double bond here. Don't let that through. Plus what? Alpha radical. So this should be M minus 15. What is mass? 86 minus 15, 71. Hopefully that's 71 it's pointing to. Why is this a good cation? Because we can do resonance. These electrons can move in here. And we can get boom, boom, boom. Okay? How many bonds do we now have between carbon and oxygen? Now I have 3. One lone pair left on oxygen. The oxygen is now positive. This is good hybridization consideration. What's the hybridization of this carbon, carbocation? Right here. How many electron regions? 2. What's the hybridization?
SP.
SP. What's the geometry? Linear. See, it's actually linear here. I just don't have it drawn right. It's linear. Okay. Problem is, if you draw it linear, you kind of need to draw into carbon or something, but it's linear. It's easier. I drew it linear there. It's just easier to draw it, but it's also linear here. All right. We just move the electrons in, and we get that resonance structure. Question: which resonance structure is major, left or right?
Right.
This one. Why? More bonds. Even though we have positive on oxygen, which might look bad, more bonds makes this one major. This cation has a name. It's kind of a cation of a carbonyl. Okay? It's called the acylium ion. All right? This is your acylium ion. Commonly formed in the mass spec of carbonyl compounds through so-called alpha cleavage, putting cation next to lone pair. It's just since we have a pi bond there already, when we do resonance, we end up with 2 pi bonds. Okay. What if we had cleaved over here? We could have gotten another acylium ion. That would have given this. We're going to leave the cation here, so we do resonance plus what? Plus a propyl radical. I'm thinking this is probably 43. What we got here? 2 carbons is 24. Oxygen is 16. That's 40. 43. It should be 43. Why was this pathway more predominant than the other pathway? They're both acylium ions.
The radical better.
But this is a better radical. Now, with carbonyl compounds, you also get something called the McLafferty rearrangement in the mass spec. McLafferty rearrangement, if you look at the mechanism, it will give you an enol. Okay? When you do a McLafferty, though, you're not cleaving to give a radical and a cation. McLafferty involves eliminating out a neutral molecule, thus you maintain your result is still a radical cation. Now, since it's still a radical cation, it's going to have the same even odd as the starting. The starting is 86. McLafferty product, since it's also a radical cation, is also going to be even. Where your other cations were odd because they're just pure cations now. They're no longer radical cations. So one way to spot McLafferty is that it's got an even molecular weight if the original was even, etc. Okay, the McLafferty I want you to do on your own. Look at it, because I asked you in the group report to discuss the McLafferty of your mass spec. I want you to look at this on your own. I'm not going to say anything else. It's a common, sort of unusual pathway. It's commonly unusual in carbonyl compounds. Please be looking ahead. We've got one more below. We'll finish this up on Friday. See what type of questions you have. We also need to have a quiz. Residents, dyings, everything we've done up to now. Yeah? See you in lab. We'll be in lab downstairs each day. Any questions, guys? Have a good day, guys.